All right, so Young's double slit experiment was an experiment that showed light to be wave-like. So what he did is he passed monochromatic light through two slits. So let's stop for a second. What do we mean by monochromatic? Mono means one, chromatic refers to color, so it's light with only one type of color, which means what about the wavelength? It's going to be the same. So if you look right here, like zoom in right here on this diagram, just boom, make this big. So what this is we have wavefront. So this diagram, here's how you look at this diagram. So this diagram here, these are called wavefronts right here. So what it is you got peak. Now what's in the middle? Trough, peak, trough, peak, like that. That's another way of showing waves. All right. So you got these waves that are only of one wavelength, so it comes from a very special light source, and the light gets passed through two slits, and then you get all these wave fronts going out. It's like slit number one, you have wave fronts from slit number one, you have wave fronts from slit number two, and if you look closely at this diagram, in fact, let's blow this up, the whole thing up real big. If you look closely, what's happening is these waves are interfering with themselves. So look, like these red dots here. So what's happening at that dot right there? We have two peaks that are overlapping. If you have two peaks that are overlapping, are they going to add or subtract? They're going to add. So you follow this out. We got constructive interference, constructive, constructive. You keep following it all the way out, and then bam, when it hits the screen, there's this viewing screen over here. There's this viewing screen over here, and where they hit, we refer to this as being a maximum, and a maximum is the same thing as a bright spot. So imagine this light gets passed through two slits, and you have this viewing screen, and on the screen you get bright, dark, bright, dark, bright, dark. Now what creates the bright? The bright, is it going to be constructive or destructive? Constructive. And then destructive, let's blow this up one more time. Because if you understand what I'm talking about right now, you pretty much have the double slit experiment down. So destructive, if you look at these right here, now what's happening right here? You have a peak and a, like let's look at this one. This one's a little easier. You look right there. So here that represents a peak, right? The wave fronts, that's the peak. And then for the other wave, it's at a trough. So if you have a peak and a trough, they're going to cancel, and then that gives you a minimum, which is known as a dark spot. Okay, so the minimums are, another name for minimum, dark spot. The maximums are the bright spots, the minimums are the dark spots. The maximums are created from constructive interference. The minimums are created from destructive interference. So big picture, what's this whole double slit experiment all about? It showed us what? That light is wave-like, because waves can add to themselves and subtract from themselves constructively and destructively. So the fact that we got this pattern, of bright, dark, bright, dark, bright, dark, tells us that light must be wave-like. Okay? Okay, so, yo. The one that I just had up?
Yes.
Yeah.
That's actually crucial.
Yeah, but it's in the book. I got that diagram straight from the book. Okay, and also these diagrams are straight from the book as well. Okay, so here's another look at the double slit experiment. So we have slit 1 and slit 2. Now look at these monochromatic light waves as they leave the slits. Notice that they are in phase with each other. So this top wave it goes peak, trough. Now what's the bottom wave doing? The same thing, peak, trough. So I'm going to use my hands here as the waves. It's like this, yo, 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 yo. Okay? All right, so they start out in phase. Now it's no big surprise, looking at this one on the left right here, it's no big surprise that as the waves travel across to the viewing screen that we get a bright area or a maximum. Now why is that no big surprise? Because the two rays are traveling the same distance. Now let's look over here at this one, over here. Now check it out. They start out in phase. Peak, trough, right? And then the ray from slit 2, peak, trough. So they start out together, right? They start out in what we say in phase. Now, what happens as they travel over to the viewing screen? Uh-oh, what happened? Do they meet the screen in phase? No. The ray from the top, this guy, the guy from the top is at a trough. The ray from slit 2 is at a peak. They meet the screen out of phase. Now, what explains how they got out of phase? The ray from slit 1, so let's call this guy ray 1, and then this guy is ray 2. Which ray travels a farther distance? Ray 1. So dude, the whole thing with this double slit experiment, whether or not the light rays from the 2 slits, whether they meet the screen in phase or out of phase, has to do with the extra distance traveled by whichever ray is traveling farther. Does that make sense? Okay. Now, just because you have an extra distance traveled, does that guarantee it's going to be a dark spot? No, because it depends on the extra distance travel. So look at this middle one here. So here, again, they start out in phase, peak, trough. This guy's peak, trough, like that. Somewhere along the way, like right about here, they're out of phase, right? This guy's at a peak, that guy's at a trough. But then what happens? They have more distance to cover, but they end up back in phase, right? So this is all about the extra distance traveled. Okay, so here's an in-depth look at the double slit experiment. So we're going to call this guy ray 1, this guy's going to be ray 2. Defining our terms, the distance between the slits we're going to call D, and then the distance from the slits to the screen is L. Theta is the trickiest part. So on the diagram, if you look at this center line from the midpoint between the slits, so I'm going to put it right there. If you draw a line from the midpoint between the slits up to the point you're focusing on, which is labeled point P in the diagram, this is theta. Now, this theta is the same as this theta. So we have these 2 equal triangles. So just be aware, in the diagram, theta is defined as the angle from the midpoint between the slits up to the point you're focusing on, but it's also this theta inside this shaded triangle right here. So those 2 thetas are identical. Now, which ray is traveling farther? Ray 1 or ray 2? Ray 2. Ray 2 is traveling farther. How much farther is ray 2 traveling compared to ray 1? Well, it turns out to be this distance right here. This distance right here is the extra distance traveled by ray number 2. And it works out as d sine theta, where d is the hypotenuse, right? Because that's the distance between the slits. D is the hypotenuse. This makes a right angle right here. So you just use trig, right? You go sine theta equals, so opposite is the extra distance traveled, so we'll just call that the extra. And then the hypotenuse is d, so the extra distance is d sine theta. Okay? Now, to get a bright spot for point P up here to be a bright spot, also known as a maximum, what has to be true about the extra distance traveled in order for that to be bright, for the waves to end up in phase? What does the extra distance traveled need to be? A multiple of the wavelength. It's got to be 1 wavelength, or 2 wavelengths, or 3 wavelengths. So what we're talking about here is the fringe order. So see here in this equation, for a bright spot, d sine theta, it has to be m lambda, where m is referred to as the order number. Okay? So like first order, second order, third order. zeroth order, m could be 0. What would that indicate if m were 0? Where would we be focusing on the screen? If the path difference, if m is 0, then that means that the extra distance traveled is also 0. So where on the screen would we be talking about there? The center point right here, because then the two rays are traveling the exact same distance. That's referred to as the 0th order. If you're smack in the middle between the slits. Okay? Now, to get a dark spot, and we're almost done, guys. To get a dark spot, what has to be true about this extra distance traveled? It needs to be equal to a 1/2 multiple of the wavelength. So it's going to be wavelength over 2, or 3 wavelengths over 2, or 5 wavelengths. So basically half a wavelength, 1.5, 2.5, 3.5. It's got to be a 1/2 multiple of the wavelength. Are you guys getting this? Okay. Okay, now. All right, so let's talk about these two equations. So these two equations are how you calculate where these bright and dark spots will appear. So the equation we just talked about, let's talk about bright fringes first. So we said that d sine theta has to be equal to m lambda to get a bright spot. If you want to calculate where it's going to appear, what we're going to do is we're going to look at this bigger triangle now, this bigger blue one right here, and we're going to say this. We're going to say that sine theta, now this is an approximation. We're making an approximation here. So sine theta, so what is sine? Looking at this blue triangle, sine is going to be opposite, which is y, over the hypotenuse. Now here's the approximation. If theta is a small angle, if theta is small, this hypotenuse right here is basically going to be L. It's going to be that distance. Here, let me show you. Let me get I'll get 2 meter sticks. So look, here is L. So this is the distance between the screens, okay? If your hypotenuse is going like that, is there much of a difference? If you have a very small angle, is there much of a difference between the hypotenuse and L? No. So the approximation that we can make is we're going to say sine theta equals y over L. That is an approximation. And we take this, plug it in up here, which is going to give us d y over L equals m lambda. So rearranging that for y gives lambda L over d times m, where m is what we call the order number. Then, to calculate dark fringes, oh, and did I use this word yet? The bright spot, dark spot, they call them fringes too. Bright fringe, dark fringe. To do it for a dark fringe, you're just going to change the m. You're going to change this part to m plus 1/2. It's a 1/2 multiple. All right? So then the final screen, I want you just to have the lingo here. So here's the lingo. So if you look at the pattern, so you get this pattern where you have this central bright spot, this guy right here. This guy is the one in the center. He's referred to as the 0th order bright. Now why 0th order? Well, that's where m equals 0. Remember, d sine theta is the extra distance traveled. So if your m is 0, there is no extra distance traveled. And the reason why is because the rays have traveled the same distance. If they travel the same distance, then d sine theta is 0. So this center guy, he's called the 0th order bright. Now, be aware that there are 2 0th order darks. there's a 0th order dark down here, and there's a 0th order dark right here. And then we get 1st order bright, 2nd order bright, and it keeps going. 3rd order, 4th order, like that. Okay? That is the double slit experiment. Now, is the double slit experiment only valid for light? Or does it also work for sound? It also works for sound. But if you're doing this with sound, instead of it being bright, dark, it's going to be loud, quiet, loud, quiet, loud, quiet. But everything else is the same. Which brings me to the handout titled In-Class Lecture Problem. So, that's it for today. And then next week we'll go over this stuff.